The mole. Now, while studying chemistry, it is not just enough to know what reagents to react to form what products. It is equally important to know how much of each reagent to use to produce what quantity of the product. We know that chemical reactions involve atoms, either free or combined into compounds. A chemical reaction may involve elements combining to form a compound breaking down into two or more products, an element replacing another in a compound to give at least two new products, and so on and so on. When we write chemical equations, they only give a simplified ratio in which atoms combine. An equation like this one only shows 2 atoms of magnesium and 2 atoms of oxygen. But chemical reactions involve millions and millions of atoms, molecules and compounds. Consider a reaction between iron filings and sulfur to form iron 2 sulfide. The equation shows a single case for 1 iron atom and 1 sulfur atom. But atoms are very small in size, so 1 teaspoon of sulfur powder contains millions of sulfur atoms. And because we cannot count these atoms, we use mole to represent a certain number of atoms, molecules or other particles in chemistry. So what is a mole? A mole is simply a specific number. In life, we might ask for 12 or a dozen of eggs, or a pair of socks for 2, or a ream of 500 sheets of paper. A mole is exactly the same. It's just a number, and it's precisely 6.02 times 10 to power 23. So we could have a mole of eggs, a mole of socks, or even a mole of sheets of paper. In chemistry, however, we use it to represent atoms, molecules, compounds, and other particles. This is because atoms are very small. It's just a convenient term to represent massive numbers. A mole is a massive number, 6.02 with another 21 zeros after it. This number was first described by Amedeo Avogadro, an Italian scientist. It represents the number of particles in 1 mole of a substance, and these particles could be atoms, molecules, ions, electrons, and so on. It is called the Avogadro's number, or the Avogadro's constant, L equal to 6.02 times 10 to power 23 particles per mole. So you see, a mole is a very large number, and the reason is because atoms are incredibly small. In half a liter bottle of water, there will be just over 25 moles of water molecules. We can therefore work out the number of molecules of water in that bottle. Remember, 1 mole contains 6.02 times 10 to power 23 molecules of water. So it's 25 times 6.02 times 10 to power 23, giving us 1.505 times 10 to power 25 molecules. And so you can see the reason why we use moles. It is a convenient way to quantify huge numbers. It is easier to talk about 2 moles of sodium rather than 1.204 times 10 to power 24 atoms of sodium. And it's easier to mention half a mole of water rather than 3.01 times 10 to power 23 molecules of water. So what exactly does 1 mole of atoms or molecules weigh? Well, this depends on just how big the atoms are. Just because we have the same number of atoms in 1 mole, it does not mean they are all the same size. For instance, you're probably aware that a hydrogen atom is much smaller than a gold atom. So 1 mole of gold will weigh much more than 1 mole of hydrogen, just in the same way that a dozen of eggs will weigh more than a dozen grains of rice. We'll look at this in molar mass next. atomic number, and mass number. When you look at the periodic table, you see that each element has its own box, and within that box you will find two numbers: the atomic number or the proton number and the mass number. The atomic number has symbol Z. This number tells us how many protons are in one atom of that element. The number is always the same for all atoms of a particular element. Atoms of different elements have different atomic numbers, meaning they have different number of protons. So an atom of hydrogen has atomic number 1 because it has 1 proton. An atom of oxygen has atomic number 8 because it has 8 protons. The next number is the mass number. It has a symbol A. It tells us how many protons and neutrons are present in one atom of an element. We know that a proton and a neutron has each a relative mass of 1, and that electrons are so small that their mass is negligible. So the mass of an atom is basically due to the mass of protons and neutrons in that atom. The molar mass of a substance is the mass in grams of 1 mole of that substance. It has units grams per mole. For any element, molar mass is equal to the relative atomic mass of that element expressed in grams. Sulfur has mass number 32. That means 1 mole of sulfur atoms will weigh 32 grams. Recall also that 1 mole of a substance contains 6.02 times 10 to power 23 particles. So it's also right to say that 6.02 times 10 to power 23 atoms of sulfur will weigh 32 grams. Also, 6.02 times 10 to power 23 atoms of iron is equal to 1 mole and will weigh 56 grams. For carbon, 1 mole is equal to 6.02 times 10 to power 23 atoms, which is equal to 12 grams, because carbon has mass number 12. So the molar mass of sulfur is 32 grams per mole. The molar mass for iron is 56 grams per mole, and carbon has molar mass 12 grams per mole. So we can say for atoms, the mass of the Avogadro number of particles is equal to the relative atomic mass in grams. Therefore, the mass of Avogadro's number of hydrogen atoms is 1 gram. The molar mass is 1 gram per mole. The mass of Avogadro's number of chlorine atoms is 35.5 grams. The molar mass of chlorine is 35.5 grams per mole. For molecules, the mass of Avogadro's number of particles is equal to their relative molecular mass in grams. So the mass of Avogadro's number of hydrogen molecules is 2 grams, and the molar mass is 2 grams per mole. The mass of Avogadro's number of chlorine molecules is 71 grams, and the molar mass is therefore 71 grams per mole. If someone asks you, what is the mass of Avogadro's number of chlorine particles? It is impossible to answer the question without the person going into further details. If by chlorine particles they meant atoms, the answer is 35.5. If however by particles they meant chlorine molecules, the answer is 71 grams. When we compare chemicals, we compare equal number of particles even though the weights are different. So if we have compounds instead of atoms, it doesn't matter how many atoms are in the formula, only the number of compound particles. Let's say you have 1 mole of iron atoms, but they are in a compound iron 3 chloride. This means you also have 1 mole of the compound. It's easy to see this Because if you have 6.023 times 10 to power 23 particles of iron 3 chloride, then it means you also have 6.02 times 10 to power 23 atoms of iron. The ratio of iron to iron 3 chloride to 1. What about chlorine atoms? The ratio is 3 to 1. There are 3 chlorine atoms per formula unit. For every mole of iron 3 chloride, there are 3 moles of chlorine atoms. So if you have 6.02 times 10 to power 23 particles of iron 3 chloride, then there will be 3 times 6.02 times 10 to power 23 chlorine atoms. For ionic compounds, the molar mass is the sum of the relative atomic masses of individual elements constituting the compound. So 1 mole of iron 3 chloride, which is equal to 6.02 times 10 to power 23 particles of iron 3 chloride, will weigh 162.5 grams. This is called the relative formula mass. The molar mass is therefore 162.5 grams per mole. What if we had iron 3 oxide? For 1 mole of iron, we have half a mole of the compound because there are 2 atoms of iron for every 1 particle of the compound. 1 divided by 2 is equal to a half. You can have half a mole of anything or even a quarter because a mole is really a very big number. This number can be broken down into smaller numbers, so it's okay to have fractions of moles. You can also double them to say that for 2 moles of iron, you have 1 mole of the compound. This is okay too, because the numbers are relative. How about oxygen? How many moles would you have? The answer is 3 moles for every mole of iron 3 oxide. Now for some calculations, we do some simple conversions. Example 1. How many atoms are there in 0.2 moles of magnesium? Remember, the Avogadro's number is 6.02 times 10 to power 23 particles per mole. Therefore, 1 mole of magnesium will contain 6.02 times 10 to power 23 atoms. The question is, 0.2 moles of the same magnesium will contain how many atoms? We have 0.2 moles over 1 mole times 6.02 times 10 to power 23 atoms. The moles cancel out and we have 1.204 times 10 to power 23 atoms. Example 2. How many atoms are there in 0.4 moles of nitrogen molecules? Again, the Avogadro's number is 6.02 times 10 to power 23 particles per mole. 1 mole of nitrogen will contain 6.02 times 10 to power 23 molecules. The question is, 0.4 moles of the same nitrogen will contain how many molecules? So 0.4 moles over 1 mole times 6.02 times 10 to power 23 molecules. That gives us 2.0408 times 10 to power 23 molecules. But remember, 1 molecule of nitrogen contains 2 atoms. Nitrogen is a diatomic molecule, and so we shall have 2 times 2.0408 times 10 to power 23, and we get 4.0816 times 10 to power 23 atoms of nitrogen. Another example. What is the mass of 1.806 times 10 to power 24 atoms of calcium. Now we know the relative atomic mass of calcium is 40. Therefore, the molar mass of calcium is 40 grams per mole. So 40 grams of calcium contains 6.02 times 10 to power 23 atoms of calcium. The question is, 1.806 times 10 to power 24 atoms of calcium will weigh how much? So we have 40 grams times 1.806 times 10 to power 24 over 6.02 times 10 to power 23. Atoms cancel out and we get 120 grams. Now we do mass to moles conversion. We have seen that molar mass is the mass of 1 mole of a substance. This is equal to the relative atomic mass of an element, the relative formula mass of an ionic compound, and the relative molecular mass of a molecular compound. Therefore, the number of moles is equal to mass in grams over the molar mass. For example, how many moles are in 2.84 grams of sodium sulfate? And you are given the relative atomic masses of sodium, sulfur, and oxygen. For sodium sulfate, the relative formula mass will be given by 23 times 2, there are 2 atoms of sodium in that formula, plus 32, the relative atomic mass of sulfur, plus 16 times 4, the relative atomic mass of 4 oxygen atoms, and that gives us 142. Therefore, the molar mass of sodium sulfate is 142 grams per mole. Number of moles will be equal to 2.84 over 142, giving us 0.02 moles.